We're going to look at the relationship between the roots of a polynomial and the coefficients of a polynomial. We'll start off with just the quadratic. So if alpha and beta are the roots, or the solutions if you like, to this equation, then it must be possible to factorise this quadratic. So it would be x minus alpha, x minus beta, and of course there'd be some constant times that, and it must be a, because we need it to be ax squared. So that would be the factorisation. Well, if I was to expand the right-hand side out, and then collect some terms, I get this. Now I'm also going to divide both sides by a, so I make them monic. Now what we saw with our polynomial results was that if you've got two polynomials that are identical to each other, then the coefficients must be identical as well. So in this one, it means that alpha plus beta, or the sum of the roots, must be the same as minus b on a. And alpha beta, the product of those roots, must be the same as c on a. So if we now had to form a quadratic equation, and we know the solutions, 2 and negative 3, well, the sum of the roots is negative 1, the product of the roots is negative 6, so therefore there's my quadratic, x squared plus x minus 6 equals 0. It's quite useful when we don't get integer solutions, when we get these conjugates, because the sum of the roots, the surd disappears and we get 4, the product of the roots, difference of two squares, so again we get rid of the surds, negative 1. So there's our quadratic, x squared minus 4x minus 1 equals 0. Well, alpha and beta are the solutions or the roots to this equation. Now we don't have to actually find the solutions, but we're interested in, and they ask the two straightforward ones usually straight away. So alpha plus beta, and we read off, oh yeah, well that's minus b on a, so it's 3 on 2. Alpha beta, well that's c on a, so it's minus a half. But then they often ask other ones. So common ones are ones like this. What's alpha squared plus beta squared? Well, if we think of our perfect square, alpha plus beta all squared, we know that's alpha squared plus 2 alpha beta plus beta squared. We can rearrange that and come up with a formula. So alpha squared plus beta squared is alpha plus beta all squared minus 2 alpha beta, and we've found those two things. So if I substitute in what we've found, we eventually end up with 13 on 4. Another common one is the reciprocal of the roots. We can't just turn the whole thing upside down. We treat it like an algebraic fraction. To get a common denominator alpha beta, the top becomes alpha plus beta. These are two things we know, so I can substitute in. So 3 on 2 over negative a half, which is negative 3. Another sort of one. They tell us some relationship between the roots, and we have to find one of the coefficients, that sort of thing. So in this one, we're told one of the roots is double the other one. What would m be? So the constant number. What would the constant number be? So instead of the roots being alpha and beta, because one's double the other, I'll say, well, one's alpha, the other one must be 2 alpha. Double the other one. So the sum of the roots becomes alpha plus 2 alpha, which is 3 alpha, and the product of the roots becomes alpha times 2 alpha, which is 2 alpha squared. I can now get a value for m, because alpha will be negative 2, sub that into the 2 alpha squared, and m is 8. I have the solution to the problem. So that was quadratics. So now let's push that idea through to any polynomial. So let's say quadratic, alpha plus beta was minus b on a, alpha beta was c on a. But with a cubic, we're going to have 3 solutions, or 3 roots. Turns out that the sum of the roots, alpha plus beta plus gamma, is still minus b on a. However, we now have another sum of the roots when we take them 2 at a time, all the possible combinations. Alpha beta plus alpha gamma plus beta gamma. But that will be c on a. But we now have a new one, the product of all 3 of the roots, alpha beta gamma. The pattern continues. It'll be d on a, but it'll be negative. So negative d on a. Push that through to a quartic. We're now going to have 4 solutions, or 4 roots. The sum of the roots is still minus b on a. When we take all the possible pairings, and there's 6 of them for this one, it'll still be c on a. But now all the possible ways we could take 3 at a time, and there's going to be 4 of those, that will still be minus d on a. But now we have this new one, when we have the product of all 4. But the pattern continues, e on a, and it's positive. So in fact, we could generalize this for any polynomial. As long as we make the leading coefficient A and then go B, C, D, E and keep going to the end of the polynomial, the formula will stay the same for every polynomial. And a shorthand way of writing it, sum of the roots one at a time. So sigma, capital sigma, we've seen that in stats, stands for sum of. And then I just write the first root down, alpha. But that means alpha plus beta plus gamma plus however many we have. But it'll always be minus b on a. If I add them up two at a time, so we still call it sum of the roots, but two at a time, all the possible pairings, that will always be c on a. Three at a time, so all the possible triples, will be minus d on a. Four at a time will always be e on a. And if we were to keep going, so if we had a pentic equation, we'd then have 5 roots. So sum of the roots 5 at a time would become minus f on a. 6 at a time would be g on a. 7 at a time, minus h on a. And you just keep going in that pattern. It alternates minus plus, minus plus, minus plus, and we just go to the next letter. That relationship we saw with the square will also hold true every time. So the sum of the roots one at a time squared will be the sum of the roots one at a time all squared minus 2 times the sum of the roots 2 at a time. And that'll be true for every polynomial, no matter what the degree is. So let's do some which are not quadratics. Alpha, beta and gamma are going to be the roots of this cubic. For some insane reason, they want us to find 4 alpha plus 4 beta plus 4 gamma minus 7 alpha beta gamma. What use it is, I have no idea. Let's find the basic information. Sum of the roots one at a time would be 5 on 2. I'm still going to find 2 at a time because that'll come in handy for some questions later on. That'll be minus 3 on 2 and 3 at a time minus a half. We now just substitute in. I've got 4 lots of the sum of the roots one at a time minus 7 lots 3 at a time. Sub in what we've found and we get our answer, 27 on 2. The reciprocal ones, I say, that's a pretty common one. Treat it like an algebraic fraction. Denominator becomes alpha, beta, gamma, we've got that. The top of the fraction in this case becomes sum of the roots 2 at a time. Sub in, and we get negative 3. There's the other common one, the sum of the roots squared. But that will be the sum of the roots 1 at a time squared minus 2 times the sum of the roots 2 at a time. Sub in what we've found, 37 on 4. Here's one from a very old HSC. This time we've got a cubic again. First thing they asked was one of the basic ones. Oh, what's alpha plus beta plus gamma? Bit of a gift mark, I guess. But you had to be careful, because notice in this cubic there is no x squared term. So the answer will be 0, because b, the coefficient of x squared, is 0. You can see people would have made the classic mistake of just going, oh, minus 3. Okay, so it'll be 3 on 1, 3. But it's the x squared term which is missing there we need. Part 2 said, find the product of the roots through all 3 of them. So that would be minus 1. The reciprocal one, as you see, these are the common questions they ask. Create the algebraic fraction. 2 at a time, we haven't worked that one out yet, but that'll be negative 3. Over 3 at a time, which is negative 1, we get an answer of 3. A little bit more recent, the 2003 question. They've told us the roots are the reciprocals of each other. We have to find the coefficient of x. If 2 of the roots are reciprocals of each other, so I'll call one alpha, the next one I'll make the reciprocal, so it'll be 1 on alpha, then the third one can be beta. Okay, there's my 3 roots. I'm going to start with the product of the roots, because if I'm dealing with a reciprocal, well, the alpha times the 1 on alpha will cancel, and I'll just get left with beta. I've found one straight away. Beta is negative 3 in this question. I'm now going to use a factor theorem, because if negative 3 is a solution, then when I substitute that into the polynomial, I should get an answer of 0. So if I sub into the one they've given me, I can rearrange this and get k straight away. I don't have to play around with sum of the roots 2 at a time and 1 at a time for this one. K ends up being 13. We can still use the other ideas of polynomials for these sorts of questions. 2006 paper. Wow. The only coefficient we know this time is the coefficient of x cubed. It's monic. R, S and T are just some real numbers. And they've told us that the solutions, or the zeros, are 1, alpha and negative alpha. Find the value of R. Well, sum of the roots 1 at a time. Well, the alpha and the negative alpha will cancel. That's nice. So R will simply be negative 1. That came out quite nicely. Find the value of s plus t. So we don't actually have to find out s and t themselves, just what they are when they're added together. Well, let's play around with the ones we haven't used yet. We haven't done 2 at a time. So if I do 2 at a time, that'll equal s. And remember, we're trying to find s plus t. So s is minus alpha squared. I don't know what alpha is, but all right. Let's have a look at 3 at a time. 3 at a time will be negative t. So t is alpha squared. But remember, we don't have to find out what s and t are. It was just the sum of the two. So if I add those two things together, I get 0. So I found the sum of s and t without actually having to find what s and t actually are. Of course, another way I could have done that one, they told me a solution was 1. So I could use my factor theorem. Sub in 1, I know I'm going to get the answer 0. So 1 plus r plus s plus t is equal to 0. We found that r was negative 1. So once again, we get s plus t equals 0. A different approach, but we come up with the same answer. Okay, that shall do us for today. So 10F, playing with the roots and coefficients of polynomials.